Welcome to Advanced Learning Tutoring. This is the chemistry playlist. Please like this video and subscribe to our channel. Ionic bonding. When a metal atom reacts with a non-metal atom, electrons in the outer shell of the metal atom are transferred. Metal atoms lose electrons to become positively charged. Non-metal atoms gain electrons to become negatively charged. Charged particles are known as ions. The ions produced by metals in group 1 and 2 and by nonmetals in group 6 and 7 will have the electronic structure of a noble gas, group 8, meaning they will have a full outer shell. The whole purpose of chemicals in a chemical reaction and bonding is to obtain a full outer shell. The electron transfer during the formation of an ionic compound can be represented by a dot and cross diagram. Dots and crosses represent electrons. The structure of ionic compounds. An ionic compound is a giant structure of ions. Ionic compounds are held together by strong electrostatic forces of attraction between oppositely charged ions. These forces act in all directions in the lattice, and this is called ionic bonding. Ionic compounds have regular structures, the giant ionic lattice. These compounds have high melting and high boiling points because of the large amounts of energy needed to break the many strong ionic bonds and overcome the electrostatic attraction. When melted or dissolved in water, known as aqueous, ionic compounds are able to conduct electricity because the ions are free to move and so charge can flow. Explaining why sodium chloride has a high melting point. This may not just be for sodium chloride, but for any other ionic compound. In an exam question, if they are asking you about an unknown ionic compound, refer to the periodic table to decide whether your compound is ionic or covalent. In this case, sodium is a metal and chlorine is a non-metal. Therefore, we know to describe the bonding of an ionic compound. To explain why sodium chloride has a high melting point, we describe the structure of sodium chloride as a giant ionic lattice. There are strong forces of attraction between oppositely charged ions, or electrostatic attraction, which requires high energy to overcome, in the form of a high temperature. Covalent bonding. When atoms share pairs of electrons, they form covalent bonds. These bonds between atoms are strong. Covalently bonded molecules are either small molecules, such as water, oxygen, and chlorine, or giant molecules made up of thousands of atoms, such as diamond, graphite, or polymers. Covalent molecules are those between non-metal atoms only. Again, as ionic, the aim of bonding is to obtain a full outer shell of electrons. Covalent molecules do this by sharing a pair of electrons. Small molecules, also referred to as simple molecules. Substances that consist of small molecules are usually gases or liquids at room temperature. They have relatively low melting and boiling points. Examples including oxygen and chlorine. This is due to the weak forces between the molecules, known as intermolecular forces. It is the intermolecular forces that are overcome when a substance melts or boils, not the covalent bond. Therefore, do not refer to bonds breaking. Refer to forces being overcome. The intermolecular forces increase with increasing size of the molecules. Covalent molecules do not conduct electricity as the molecules have no overall electric charge and no free-moving electrons. Explaining why chlorine is a gas at room temperature. In terms of an exam question, you may not get a question that refers to chlorine specifically. It may be carbon dioxide or ammonia, or any other simple covalent molecule. Refer to your periodic table to decide whether we have a metal or non-metal, to deduce the type of bonding. Chlorine is a non-metal, therefore we are referring to a covalent molecule. So we think about why simple covalent molecules tend to have low boiling points and melting points. Chlorine is a small molecule, or a simple covalent molecule. It has weak forces between the molecules, or it has weak intermolecular forces, and these forces are overcome easily with little energy. Why does carbon dioxide have a higher boiling point than oxygen? In terms of an exam question, you may not have the specific examples of carbon dioxide and oxygen. It may be fluorine and iodine, for example. But what we want to decide is the type of bonding, so refer to your periodic table to deduce the type of bonding by deciding whether your substances are metals or non-metals, or a combination of both. In this case, carbon dioxide and oxygen are giant covalent molecules. Polymers have very large molecules. Polymers are long chain molecules, typically formed from carbon and hydrogen atoms. The atoms are linked by strong covalent bonds. The intermolecular forces are relatively strong, and so are solids at room temperature. Silica, diamond, and graphite are other examples of giant covalent molecules, with high melting and boiling points due to the strong covalent bonds that must be overcome. Giant covalent molecules are typically formed of thousands of atoms. Allotropes of carbon. Allotropes of carbon are different forms of how carbon can bond to itself. The different forms of carbon are diamond, graphite, graphene, and fullerenes. Firstly, it's important to understand the bonding of carbon. Carbon is in group 4 of the periodic table. It has 4 electrons in its outer shell and will want to form 4 covalent bonds to obtain a full outer shell of electrons. In diamond, each carbon atom forms 4 strong covalent bonds with other carbon atoms. Diamond is hard, has a high melting and boiling point, and does not conduct electricity as there are no free-moving electrons. Graphite. In graphite, each carbon atom forms 3 strong covalent bonds with other carbon atoms, forming layers of hexagonal rings which have no covalent bonds between the layers. These layers are able to slide over each other, making graphite soft. 1 electron from each carbon is delocalized, and so graphite conducts electricity. Graphene is a single layer of graphite and has properties which make it useful in electronics. Similar to the structure and bonding in graphite, each carbon atom in graphene has 1 delocalized electron, meaning graphene will conduct electricity. Fullerenes are molecules of carbon with hollow shapes, either spheres or tubes. These are useful for drug delivery and electronics. An example of a fullerene is the Buckminster fullerene. It has the formula C60, meaning it is made up of 60 carbon atoms. The limitations of the models that represent the bonding in compounds. The bonding in compounds can be represented by a number of different models. The dot and cross model, ball and stick, 2D or 3D models. In the dot and cross model, electrons appear as dots or crosses, when in fact all electrons are the same and should not be represented as different shapes. However, this makes it easier to identify the electrons in specific atoms. In the ball and stick model, it does not represent the shape of the model and presents a bond as a physical stick, when in fact bonds are the sharing or the transfer of electrons. In the 2D model, there is no representation of the shape of the molecule, but it does show the atoms that are present. In the 3D model, it represents the shape of the molecules in three-dimensional space, but shows atoms as solid spheres, which we know to be incorrect. Metallic bonding. Metals consist of giant structures of atoms arranged in a regular pattern or lattice. The electrons in the outermost shell of metal atoms are delocalized and so are free to move through the whole structure, therefore conducting electricity. The sharing of delocalized electrons give rise to strong metallic bonds. In metallic bonding, there is a regular pattern of positive metal nuclei surrounded by a sea of delocalized electrons. It is important to note that metallic bonding does not occur between metals. It is the structure and bonding within each individual metal. Metals and alloys. Alloys are a mixture of different metals. In pure metals, atoms are arranged in layers, which allows metals to bend and be shaped, as the layers are able to slide over each other. This is due to each individual atom having the same atomic radius and the same sized atom. Pure metals are too soft for many uses, so they may be mixed with other metals to produce an alloy. In alloys, the metals have different sized atoms. This distorts the layers, hence there are no clear layers that are able to slide over each other, giving them different properties to pure metals, for example being stronger. Nanoparticles. Nanoparticles are smaller than fine particles. They are between 1 and 100 nanometers in size. As the side of a cube decreases by a factor of 10, the surface area to volume ratio increases by a factor of 10. Nanoparticles have a larger surface area to volume ratio than fine or coarse particles. Therefore, smaller quantities of nanoparticles are needed to be effective. Nanoparticles have many applications in medicine, electronics, sun creams and catalysts. An advantage of nanoparticles is that smaller amounts are required. A disadvantage, however, is that nanoparticles are small enough to be absorbed into the skin.